Okay, let's check volume. Okay, we're okay now. So the equilibrium constant Kp, this is the first problem I'm going to solve, for the reaction is 200, there it is, Kp, let's write our data, 223 at a certain temperature. It doesn't say the temperature, but we don't need it here. So it's asking calculated the partial pressure of O2 if the partial pressure of NO is 0.597. They're giving this in equilibrium. And the PNO2 equals 0.215 atmosphere. And this is atmosphere, and this is atmosphere. So let's go ahead and solve it. And it's not very difficult, but then thing is that you have to write the expression. Kp, the equilibrium expression, and is the products over the reactant. In this case, it's the pressure, so it would be the partial pressure of O2 multiplied by, we can do the multiplication sign, multiply by the partial pressure, okay, of NO2, of NO, sorry, to the square, because it has a coefficient here. And on the bottom is always the reactant, and it would be the partial pressure of NO2 to the square. Don't forget to put always the square for the reactant. So we got here, it's asking to calculate the PO2. So we take this, Kp, super easy, multiply by PNO2 to the square. Okay, and we divide it by, because what we want is the partial pressure of oxygen 2. So we're going to divide it by PNO2 to the square. And that gives me the partial pressure of O2. So let's plug in the number. And the partial pressure of O2 would be equal to, okay, what is the Kp? Kp says 223. Okay, so it's going to be 223 multiplied by partial pressure of NO2. NO2 goes in the top because it's the reactant now goes in the top, was on the bottom. On the bottom. So this would be, NO2 would be 0. Be careful when you pick up the numbers. Make sure it's the right data. Okay, the right one. And if you look at this, this would be 0.215. That's right. And it's going to be to the square because the NO2 has a coefficient of 2. And then here would be, I made a mistake here. Sorry for that. That it's this one on the bottom is the NO. Okay. Maybe you realize it already. This one is the NO. When I change it, the expression is correct. It's right. But when I change the here, I put it double. I rewrite it again, this one. And it's, watch, the partial pressure of NO2 goes on top, multiplying the Kp and to the square. And if we want this by itself, this would be on the bottom and to the square. So what we're going to plug in here is the NO2. NO, sorry, to the square. And it's this one, 0 point, and to the square, remember, NO has a coefficient of 2 also. 0.597 to the square. So this, all this, gives you, I had the numbers here, 28.9 atmosphere. Should give you 28.9 atmosphere. Okay, let's do more here. Let's do the next one. And the next one is for the reaction, okay, um, for the reaction, this is a little bit longer, but it's not bad. It's easy. For the reaction, N2 plus nitrogen produces ammonia. The production of ammonia. Kp, they're giving you the Kp at 493 Celsius. What is Kc of the reaction? Now, the easy way to do it, and this is the best, is that Kp, using this, is Kc multiply by 0.0 by, let me, instead of plugging it in, sorry, by RT to the different in moles. Okay, this is the difference in the coefficient. Delta N would be moles of the reactant, the product, sorry. This would be the moles of the product, and I don't want to erase it. Delta N would be the sum of the moles of products minus the sum of the moles of reactants. Okay, so we got here, okay, to find out the Kc, this equation comes really from the expression of Kc, or K is also called, that is the concentration of the products divided by the concentration of reactant. And it comes from, if you have here, for example, using the ideal gas equation, equals nRT. And basically when you plug in, okay, you want to take it to Kp, right? You're going to go ahead, P equals nRT divided by the volume. But N over the volume is concentration, right? So P would be the concentration of the gas multiplying by T. So that's it's where it's coming from. Because this Kp, or that would be the pressure of the reactant divided by the pressure of the pressure of the product, sorry, divided by pressure of the reactant. And that means that when you're going to plug in the Kp, right, it's going to give you the concentration by RT, and so on. So it means that this, the expression for the concentration is the Kc. Conclusions. It comes from using this equation, no more complications. It comes from using this equation, okay, in the Kp and Kc expression, and you're going to get this little equation. I don't think they're giving it to you in the formulas, in the formula sheet, but if you can learn it by memory, it would be ideal. So let's go ahead and let's use the formula, okay, and come I'm gonna do something even if it takes a little bit. I'm gonna pause it while I erase this. Okay, let's do something better. What I did is basically substitute everything so you could see where it's coming from. And basically is Kc where this expression, this equation is coming from. And it's Kc is the products divided by the reactant, the concentration. But you know that PV equal nRT. So if you take the volume to the bottom on the next one, N over V equal P N over V multiplied by RT. So we divide P by RT. So this would be the concentration, right? Now, if you plug in to the expression of concentration, concentration is the pressure of the Na3 divided by RT each one. You see it, instead of using concentration, I'm going to plug in the expression of the gas law, ideal gas law, P over RT, the partial pressure of each gas. Doing that, I get this expression, right? As this is a constant, I take it on as a common denominator, and it gives me 1 over RT. In this case would be minus 1 because we have more moles of reactant than product. Meaning that if you look at this is 2 minus 3 plus 1, negative 1. No, negative 2. Negative 2 would be this. Okay, negative 2. So that means that 4, yeah, this would be 2, that's why. This would be 2 for 2 minus 4, negative 2. So if you take it on the other side, that's what they get the expression, the equation. So let's go ahead and keep, but this is not important. It's just to understand where you get this little equation. If you're able to memorize it, that would be better. Others do it all, other literature and books do it all, the whole thing. But let's go ahead and plug in the values. So Kc, they're asking for the Kc. So you can do this. Kc equals the Kp divided by RT, okay, to the delta N. Now, let's first calculate delta N. And delta N, like I was saying, for this would be the sum of the moles or coefficient of the products, which is 2, minus the sum of the reactant, which is 4. So delta N would be negative 2. Negative 2. Now, RT, Kp would be, the Kp is given, that would be 0.00879. The other thing we have to do is convert 493 Celsius plus 273 equals 766 Kelvin. So plugging in Kc equals Kp 0.000879 divided by 0.082. You can use it. It depends if they give you the constant with the 0.05 with more decimal, use the one they're giving you. Okay, you need to use the one they're giving you. Multiply okay, and multiply by 766 Kelvin to the negative 2. To negative. And that is going to be, okay, Kc equals 0.000879 multiplied by 0.0821 by 766 to the square. So the value of Kc gives you 3.48. And this is our answer. Okay, the next problem. Given the value of Kc, calculate the equilibrium constant for the equation B. And we have to look. It's very similar to the Hess law, but with equilibrium, you don't add the K's, you multiply. So let me give you the three basic rules. And it's like, if you add the equation 1 plus equation 2, or subtract, right? You multiply the K's. If you flip the equation, right? Equation 1 would be minus equation 1, meaning that you flip it. Okay, something I made up now would be 1 over K1. You don't change signs or anything. It's 1 over the constant. And finally, if you multiply an equation, right, by a coefficient, you square it, or that's the exponent. You multiply by 3 would be k to the third, and this would be to the square. Okay, so let's do it this one, okay? And what we have to look is that they're asking for the Kc of this, and you look at what is the difference between these two. The difference is that here, right, you multiply by 3 to eliminate this. So do you see you got 302, 02, multiplied by 3 cancels out the 3 fraction, I2. So the Kc, if you multiply by 3, would be the other Kc, right? 9.74 times 10 to the negative 9 to the cube. Kc would be equal to 9.24 times 10 to the negative 25. And that's it. Let's go with the next one. Okay, this is very similar to the other one. It's just practicing. What do we do with the K? So calculate the equilibrium constant at 1123 Kelvin for the reaction. The temperature has nothing to do with anything. It's always given. Write the equilibrium constant expression. Well, not always. Majority of the time. Almost always. So you need to write the Kp expression, okay, and calculate it. We can calculate it because we have values of both for this equation. And if you see, this equation is the sum of these two. But we need to do several things. And one is, okay, if you keep CS on the carbon solid is on the left and CO2 too. Okay, so the equation is 9. Now on the bottom, on the right side, watch what we're going to do here. This plus CO2 gas, hold on, okay, 2 CO gas. Now this one, the Cl is on the left, and there's no more Cl, and it's with a 2, so we're going to have to multiply this one by 2, plus, sorry for that guy, Okay, so this would be gas. Okay, then we have plus 2Cl2 gas. Remember, we were multiplying the whole equilibrium equation. For the whole equation, we're multiplying by 2. Yes? Okay. So this stays the same. So let's see if we get the equation that we wanted. And it's yes, because CO and CO cancels out. So we're going to get CS plus CO2, here it is, plus gas plus 2Cl2 gas gives me 2, and this is supposed to be the same, 2 COCl2 gas. Now let's look at the constant, because this would be the Kp total. Let's put it like that, to put something different. So the first one, the first Kp, right, stays the same. Okay. Kp stays the same because you didn't do anything with that equation. 1.30 times 10 to the 14. On the second one, we have a little bit of problem. This is 14. Well, a little bit of problem. And what we did is just multiply by 2. So the second one would be the Kp2 to the square. So the total, the Kp total, is down here, would be equal to the Kp, doesn't move, it's the same, remember the first one, and the second one multiply. Remember, if we add them, we multiply both, but this one, it has to be to the square, and that is going to be our final answer. So the total by Kp would be, let me look at the numbers, 1, the new K, the total for this equation would be, or we can call it Kp3 or Kp3. So it would be the first one, that is 1.30, that doesn't change, right? By 10 to the 14. Yes? And the other one is 6.0 multiplied by 6.0 times 10 to the negative 3 and to the square. So the Kp final, 3, doesn't matter, okay, would be equal to 4.68 times 10 to the 9. And I mean, doesn't matter because you can call it whatever, but you need to know that the Kp that we're at for finding out and calculating is the Kp for this for this reaction. Yeah, and that is your answer. Oops, sorry.